All right, welcome back to our um, section on confidence intervals. We're going to take a look at confidence intervals for population mean. We'll look at some examples in this video. In our last one, we took a look at the concepts of it. So let's actually get our hands dirty here, so to speak, and actually create some confidence intervals. So example one, we have the waiting time of a sample of 100 patients at a hospital is 3.5 minutes with a standard deviation of 0.75 minutes. Sample standard deviation of 0.75 minutes. Construct a 95% confidence interval for the mean waiting time of all patients at the hospital. So, again, we don't have necessarily all the patients who have ever been to this hospital as far as their waiting time is concerned. So, we're going to create a 95% confidence interval for the mean waiting time. So, we have our mean waiting time for our sample plus or minus our z alpha over 2. And again, because we have 100 patients, we can use our sample standard deviation for that. When we get into hypothesis testing, we'll see what happens when you have less than 30 in your sample. So we'll worry about that in the future. And then the square divided by the square root of our sample size. So when we plug in the numbers, 95% confidence interval, we had that table to expedite the process. The critical value here for z of alpha over 2 for 95% is 1.96. So again, we can get the normal distribution and calculate the area that's outside, or get the z-score for the area that's outside, and it should give us about 1.96. Sample mean of 3.5, and then our sample standard deviation of 0.75 over the square root of our sample size of 100. And just to show you the calculation here, 1.96 times the standard error is 0.147. So our margin of error for our population mean waiting time, our margin of error here, this 0.147 or 0.147 minutes, that means that we have 3.5 minutes for our sample mean with a margin of error of 0.147 minutes, which will give us between 3.353 minutes to 3.647 minutes. So a 95% confidence interval for our population mean waiting time is 3.353 minutes to 3.647 minutes. So we can be 95% confident that our population mean time is between 3.353 minutes and 3.647 minutes. So we can also use computers and all that to do this for us. I'll link this code in the description, but we have our imports here, typical imports. Here I have my X bar is 3.5 minutes, my standard deviation is 0.75, my sample size of 100, and the confidence level is 95%. So make sure you enter it as a decimal. And if I run this, here's my 3.353, and then here's my 3.647. So this one just goes out a lot more decimal places than the answer did. But we get our lower value for our confidence interval and our upper value for our confidence interval as well. So we can look at using the computer here in the program for calculating these as well. So, all right. Oftentimes, the margin of error, the 0.147 that we looked at in the last example, are going to be graphed as error bars, what are known as error bars on a visual display. So, for instance, here I have a bar graph for example 1. I didn't really think of what to label it, so I could have labeled it hospital here, but whatever. Our mean waiting time is the height of the green bar. So, the height of this green bar is at 3.5. Our margin of error, the upper value 3.5 plus 0.147, and then the lower value 3.5 minus 0.147, are represented by this vertical bar that looks like a capital I. So the bigger the margin of error, the longer or taller, I should say, that this bar is going to look. So oftentimes you might see bar graphs with these these error bars in here, and that's what they're used to represent, margin of error. Now, be advised, though, that some graphs use standard deviation for their error bars. So hopefully whoever designed the graph if they're using error bars in it, there's some description somewhere that tells you that the error bars represent margin of error versus standard deviation. So again, going back to our visual displays of data and what makes a graph good is try not to be deceptive and make sure if you're using standard deviation, or even if you're using margin of error, it never hurts to let your reader or your audience know what exactly you are using in your graph. All right, example 2 is suppose we take a sample of 45 gas prices, find the mean price per gallon is $2.45, which may or may not be good depending on when you are watching this and what the price of gas is. And the standard deviation in our sample is 12 cents a gallon. So create a 98% confidence interval for the population mean price per gallon. So I have it all worked out here in terms of using the calculations, but we'll use the computer as well. And if you want to watch the calculations, I guess just go back and pause it at the right time and write it all down. But we'll do this example on the computer. So we got 2.45. Most technology and statistical programs will be able to calculate confidence intervals for you anyway. Standard deviation of 12 cents. So this time our standard deviation is 12 cents. We have 45 in our sample size, so we'll change that. And then our confidence level this time is 98. So it's going to give us some long decimals. We'll just round to 2 decimal places, as is typically the case with money. So we got about $2.41, rounding this up, $2.41 to $2.49. So I'm just going to go through these real quick. So 98% confidence interval for the mean population price per gallon is between $2.41 and $2.49. All right, part B, what would the confidence interval be if the sample size was increased to 100? So not changing the confidence level or anything else, but just changing our sample size to 100, what we end up with is about $2.42 to about $2.48. So about $2.42 to $2.48. So we didn't change anything except the sample size. So keeping the confidence interval the same, what happens as we increase the sample size? Well, increasing the sample size decreases the standard error, which is going to decrease the width of our confidence interval. So we went from $2.41 to between $2.41 and $2.49 to now between $2.42 and $2.48. So again, the more we get in our sample, the better it will represent the population, which means now we've narrowed down where we believe the population mean to be, or what we believe the population mean to be, simply by increasing our sample size and not having to increase our confidence level. So again, it's very beneficial to get as big of a sample, random sample as you can that represents the population. So we're going to conclude this video by discussing what the confidence interval is not. We've talked about what it is. Let's talk about what it's not. So the following here are incorrect interpretations of a confidence interval. So part 1 here is there is a blank percent chance that the population mean is in this interval. So in our last example, we would say that an incorrect interpretation would be that there is a 98% chance the population mean is in any one of those 2 intervals from the previous couple problems. That is an incorrect interpretation. There's a difference between being confident, 98% confident, versus there's a 98% chance. So in terms of incorrect interpretations, we don't say there's a 98% chance or 95% or whatever percent chance that the population mean is in that particular interval. Also, it is incorrect to say that there is a blank percent chance that the population mean is going to be whatever our sample mean is. So in our previous example, we had a sample mean of $2.45 for the price per gallon. We would be incorrect in saying that there's a 98% chance that the population mean is $2.45. That is, again, is not a correct interpretation of what confidence intervals are. Confidence intervals, that percentage, again, represents if we were to repeat that experiment with that same population and same sample size that we draw each time, then we would see like 98% of our confidence intervals would contain the population mean. So in this case, 98% of the confidence intervals we create would contain the population mean price per gallon, whatever that happens to be. So, all right, that about does it for this video. Thanks for watching. I'll see you next time.